Do you remember rational functions in Math 20-1? Probably not. Yeah, but Chapter 9 is actually going to build upon what you learned in Math 20-1. So you're probably saying, well, I don't remember what a rational function is. Oh my gotcha, oh my gotcha. Don't worry about it. Look at the root of the word. The root of the word is ratio. Ratio meaning fraction. Now I kind of remember this. Remember these guys? These are the ones that have polynomials in the denominator. So polynomials could be a numerator and a denominator. Take a look. Look at the rational function definition from your book. The rational function definition from the book says a function that can be written in the form of, look, P of x over Q of x. So I wrote it right over here. Look at this. So what does this mean? Do you remember that can of worms that this thing opens up? This opens up a pretty nasty one. The reason why is because of the Q. The Q, being that it is a polynomial, may have a chance of becoming 0. And you know and I know, as soon as you have a fraction, for example, like this one, and that denominator is 0, well, they love to say in the math world, it's all fun and games until somebody divides by 0. You can't have a 0 in the denominator. Now, if you remember what that means then, okay, is that these become something called non-permissible values. So if you look, this says denominators can't be 0. Any value which makes the denominator 0 is not allowed. That's why we call them non-permissible. They don't have permission. They're not allowed to have a number that makes the polynomial and denominator a 0. Oh my goodness. Well, okay, hold on. What does that mean for us later on? Well, what it means for us later on is that it brings up the whole idea of asymptotes. Yes, do you remember that? Oh boy. Okay, so how do we figure out the non-permissible values? Well, I got 4 beautiful questions here for you. Let's take a look at them. Some of these questions super easy, like the first one. Notice that this is a rational function. Why? Because it has a variable at top and a variable on the bottom. Yay. So that means that variable on the bottom may have a non-permissible value. Well, gee, all you got to do is say, oh, n cannot equal to 0. You're done. That's it. Think about it. If we let this guy equal to 0, we're dividing by 0. Boom. No, you can't do that. So you say n cannot equal to 0. How do you find this one then? Well, simple. Just go x plus 4 cannot equal 0 and solve it. Subtract 4 from both sides. Look what you got. You got x cannot equal to minus 4. There's your non-permissible value, because if you put in minus 4 into there, minus 4 plus 4 gives you a 0. Not allowed. Now, I'm going to skip C for a second, and I'm going to get back to that one in a minute. I want to look at one like this. Cool. Okay. Look, there's our fraction. So again, look at that denominator and say, because your denominator, you're not allowed to equal to 0. Solve it. Add 2 to both sides, and guess what? X cannot equal to 2. There's your non-permissible value. But do you remember what happens in something as ugly as this? Yes, it's a trinomial. Well, folks, guess what? You're going to have to go back, and you're going to have to remember how to factor. Go all the way back to Math 10C. So this should be easy for you. Yes, PSA. And if you remember, you should actually remember how to do this by just looking at it. I'm not saying that you should do it just by looking at it, but goodness gracious, these are easy. Okay? Reason why? Look for 2 numbers whose product, that's what the P stands for, multiplies to give me 10, whose sum, that's what the S stands for, adds up to 7. So in other words, look at all the products. 10 and 1. Great. 2 and 5. Which one of those adds up to 7? Of course, 2 and 5 does. Yes. So your answer is 2 and 5. So what do you do with this mess? Real easy. You factor it. This is x plus 2, x plus 5, and you say, okay, since that's the denominator, doesn't equal to 0, right? So you look at them individually and say x plus 2 does not equal to 0, x plus 5 does not equal to 0. Bring that over, you find out that x cannot equal to minus 2 and x cannot equal to, in this case, minus 5. Sorry for the overlap there, right? So this guy actually has two non-permissible values. Now, what do those non-permissible values mean? Hey, you got to stand by, take a look at the next podcasts. But for right now, does this mean that everybody has non-permissible values? No. There are some rational functions that do not have Npvs, as said by this little note. Let me show you why, right? Take a look at this guy. If you try to determine the Npv of this guy, this is x squared plus 1 cannot equal to 0. Bring the 1 over. Look, x squared cannot equal to negative 1. Can you square root a negative number? No. So guess what? This does not have any Npvs. Think about it for a second. Let me erase this and let me show you why. Can you figure out any number that we can put, any real number that we can put in x, square it, add it to 1 and get 0? No, neither can I. Okay, so this does not have an Npv. Fascinating. And that ends up making all kinds of interesting things happen. Oh, we'll get to that later on. Ooh, I got some stuff to show you. Oh, baby. Same thing goes with this one. X squared plus 4, say cannot equals to 0. Bring the 4 over, and look what happens. It becomes negative 4, and again, you can't square root this. So this doesn't have Npvs either. Take a look at this one. Same kind of nonsense. Say, can't equal to 0. Bring the 6 over. You got 3x squared cannot equal to negative 6. Divide by 3. Divide by 3. Look, x squared cannot equal to minus 2. Try to square root that. You can't. So this doesn't have any Npvs either. So look for a couple of things. You should notice a pattern in every single one of these. Every single one of these has a squared in it. You see it? Do you see the squared in the denominator? There it is. And then the other thing that you should notice here is that when you bring this guy over, it becomes a negative, which means you can't square root it. Aha, so there's the pattern. Look again, this goes over, becomes a negative, can't square root it. This goes over, becomes a negative. Even though you divide it by 3, it's still a negative and you can't square root it. Okay, so what does this lead to? All of these Npvs lead to something very, 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 very important. Now, I'm just going to touch on it in this podcast, but you got to stay tuned to other podcasts to find out what it's all about. Okay, so graphing and Npvs. Here we go. Remember, Npvs could give you, and this is primarily what we did in Math 20-1. In Math 20-1, we said the Npvs give us something called a vertical asymptote. So what we did is we graphed, we went, okay, there's my x-axis, there's my y-axis, and I had something that comes around like this, and it went around and went something like this, and then I said, oh my goodness, there's the non-permissible value that gave me this wonderful thing called an asymptote. And it said that this curve gets close to that line but never touches it. This curve gets close to that line but doesn't touch it. That's what an asymptote was. Okay, that specifically was a vertical asymptote. Well, now, what you're also going to find out is that this could lead to something called a point of discontinuity. Now, I don't want to talk about this too much, but the cool thing is this is going to make a hole in your graph, and you're going to go, yes, okay? It's really, really cool stuff. So, all kinds of neat things to know about here, and they're all going to be explained in upcoming podcasts.